Our journey begins in the vast expanse of space within colossal clouds of gas and dust known as nebulae. These magnificent structures, often appearing as colorful ethereal shapes, are the cradles of creation in the universe. They are the places where the raw materials of the cosmos come together to form new celestial bodies. These stellar nurseries, often spanning light-years across, are the birthplaces of stars and their planetary systems. Within these vast regions, the delicate dance of gravity and pressure sets the stage for the formation of new stars. Over millions of years, these processes gradually transform the nebulae into the brilliant stars that light up our night sky. Nebulae are composed primarily of hydrogen and helium, the most abundant elements in the universe, along with traces of heavier elements forged in the hearts of long-dead stars. These heavier elements, such as carbon, oxygen, and iron, are the building blocks of planets and life itself. They are the remnants of previous generations of stars that have lived and died, enriching the cosmos with their elemental gifts. These elements, scattered throughout the cosmos by stellar explosions, provide the building blocks for future generations of stars and planets. When a massive star reaches the end of its life, it explodes in a supernova, sending its enriched material into the surrounding space. This material then becomes part of the next generation of stars and planets, continuing the cycle of cosmic evolution. Within these swirling clouds, gravity acts as a cosmic sculptor, drawing matter together and causing regions of higher density to form. These regions, known as molecular clouds, are the birthplaces of new stars. As gravity pulls more and more material into these regions, they become denser and hotter, setting the stage for the next phase of star formation. As these regions collapse under their own weight, they heat up, creating pockets of intense energy. This process, known as gravitational collapse, is the first step in the formation of a new star. The collapsing material forms a protostar, a hot, dense core that will eventually ignite nuclear fusion and become a full-fledged star. When the temperature and pressure at the core of such a collapsing region reach a critical threshold, a star is born. This moment, when nuclear fusion begins, marks the birth of a new star. The energy released by fusion causes the star to shine, lighting up the surrounding nebula and heralding the arrival of a new member of the cosmic family. The birth of a star is a dramatic event marked by the ignition of nuclear fusion in its core. As hydrogen atoms fuse to form helium, immense amounts of energy are released, causing the newborn star to shine brightly. This intense radiation illuminates the surrounding nebula, creating breathtaking displays of cosmic beauty, such as the Orion Nebula, a stellar nursery visible to the naked eye. As the young star ignites, the remaining gas and dust in the surrounding nebula begin to swirl around it, forming a flattened disk known as a protoplanetary disk. This disk, composed of the leftover material from the star's formation, will become the birthplace of planets. The protoplanetary disk is a dynamic environment shaped by a complex interplay of forces. Gravity pulls material towards the central star, while centrifugal force, generated by the disk's rotation, pushes outward. This balance of forces keeps the disk from collapsing onto the star and allows planets to form within its confines. Within the disk, tiny dust grains, remnants of the original nebula, collide and stick together through electrostatic forces. These initial clumps, no larger than grains of sand, mark the first step in the planet-forming process. As dust grains continue to collide and stick together, they gradually grow larger, forming pebble-sized objects, then boulder-sized, and eventually, kilometer-sized bodies known as planetesimals. This process, called accretion, is driven by a combination of factors, including gravity, electrostatic forces, and the random motions of particles within the disk. Planetesimals, with their larger mass and stronger gravitational pull, begin to attract smaller objects in their vicinity, further accelerating their growth. Over millions of years, these collisions and mergers shape the protoplanetary disk, transforming it from a smooth, dusty disk into a chaotic collection of planetesimals of various sizes. Section 5. Planetesimals to protoplanets, a gravity-driven dance. As planetesimals continue to grow, their gravitational influence becomes increasingly significant. The larger planetesimals, with their stronger gravitational pull, begin to attract and accrete smaller ones, leading to a runaway growth process where the largest bodies grow the fastest. This gravitational interplay between planetesimals results in a cosmic dance, with objects colliding, merging, and sometimes being flung out of the protoplanetary disk altogether. Over time, this process whittles down the number of planetesimals, leaving behind a smaller number of larger bodies known as protoplanets. Section 6. The formation of layers. Differentiation in protoplanets. As protoplanets grow larger, their internal structure begins to change. The heat generated by radioactive decay within their interiors, combined with the energy released from frequent collisions, causes these bodies to heat up and melt. This melting allows materials of different densities to separate, a process known as differentiation. Denser materials such as iron and nickel sink towards the center, forming a metallic core. Lighter materials such as silicates rise to the surface, forming a rocky mantle. This differentiation process is crucial for the development of planets, as it gives rise to their internal structure and ultimately influences their surface features. Section 7. Atmospheres and oceans. The emergence of habitable worlds. As protoplanets cool and solidify, their surfaces and atmospheres continue to evolve. Volcanic activity releases gases from the interior, forming primordial atmospheres. These early atmospheres can be quite different from those found on planets today, often consisting of gases like methane, ammonia, and water vapor. In some cases, water vapor in the atmosphere condenses to form oceans, while other volatile compounds such as carbon dioxide can be trapped in rocks or lost to space. The presence of liquid water is considered a key ingredient for life as we know it, making the formation of oceans a pivotal step in the emergence of potentially habitable worlds. Section 8. A universe of diversity. The vast array of planetary systems. Observations of other planetary systems have revealed an astonishing diversity of worlds, from gas giants larger than Jupiter, which dwarf even the largest planets in our own solar system, to rocky planets smaller than Mercury, which challenge our understanding of planet formation and survival in harsh cosmic environments. This diversity highlights the complex interplay of factors that influence planet formation, including the initial conditions in the protoplanetary disk, where dust and gas coalesce under gravity to form new worlds, the mass of the central star, which dictates the gravitational pull and energy output that shape the orbits and climates of surrounding planets, and the gravitational interactions between planets, which can lead to dramatic shifts in their orbits and even collisions that reshape entire systems. Some planets orbit their stars in tight circular orbits, hugging their stars so closely that their years last only a few days, while others follow highly elliptical paths, taking them on long, looping journeys far from their stars and back again. Some systems are home to multiple planets crammed into a small region around their star, creating a crowded and dynamic environment, while others have planets scattered far apart, with vast stretches of space between them, making each planet an isolated world. This diversity underscores the vastness and wonder of the cosmos, reminding us of the endless possibilities that exist beyond our own solar system, suggesting that our own solar system is just one example of the countless planetary systems that likely exist throughout the universe, each with its own unique characteristics and mysteries waiting to be discovered. Section 9. An ongoing process, planetary formation in the cosmos. Planetary formation is an ongoing process, with new stars and planets constantly being born in nebulae throughout the universe. These vast clouds of gas and dust, known as stellar nurseries, are the birthplaces of stars and planets. Within these nurseries, gravity pulls material together to form dense cores, which eventually ignite to become new stars. Surrounding these young stars are protoplanetary disks, swirling masses of gas and dust that coalesce to form planets, moons, and other celestial bodies. By studying these stellar nurseries and the protoplanetary disk that surround young stars, astronomers can gain insights into the processes that gave rise to our own solar system and the countless other planetary systems that likely populate the cosmos. Observations of these regions help scientists understand the conditions and mechanisms that lead to planet formation, shedding light on the diversity of planetary systems and the potential for habitable worlds beyond our own. As we continue to explore the universe with increasingly powerful telescopes, we can expect to discover even more diverse and intriguing planetary systems, providing further clues to the origins of planets and the potential for life beyond Earth. These advanced instruments allow us to peer deeper into space and time, capturing images and data that reveal the complex and dynamic nature of planetary formation. Each new discovery adds a piece to the puzzle, helping us understand the myriad ways in which planets can form and evolve. The journey to understand planet formation is far from over, but each new discovery brings us closer to unraveling the mysteries of our cosmic origins. As we continue to push the boundaries of our knowledge and technology, we remain ever hopeful that one day we will fully comprehend the intricate dance of forces that give rise to planets, stars, and the very fabric of the universe itself.